Good morning. This is the fourth lecture for geography from Possible IAS Institute. So, in today's lecture, we will start with the rocks and rock properties. What are the different types of rocks? What is the rock cycle? We will start with that, and then later we will continue to earthquakes and interior of the earth and volcanism. Okay. And if time permits, we will then continue with the continental rift hypothesis by Alfred Wegener. So, let's begin with the first one, that is rocks and minerals. So, what are minerals? First of all, minerals are inorganic solids with a definite chemical composition. So, these are the three properties of minerals. That first of all, they are inorganic, they're solids, and they have a definite chemical composition. So, different elements, they combine to form minerals, and then the minerals combine to form rocks. Okay, so this is how different rock types are formed with the help of different minerals. Okay, so now we have to know what type of minerals are there in the earth. So first of all, we will begin with the different properties of minerals. Okay, so when you hear the term hematite, when you hear the term quartz, when you hear the term feldspars, we are talking about minerals. Okay, so now we will there is a set of properties of minerals that has been given even in the NCERT for class 11th. So we will discuss the ones which are important from them. So first of all that we will study is cleavage. Okay, so first of all, first thing is cleavage. So in cleavage, what happens is that certain minerals, they break along particular planes. Okay, so they split easily, they break along easily along particular planes. So like if you see mica, what happens is it has thin sheets. Now these thin sheets, they come off layer by layer. Okay, so that means mica has a perfect cleavage, that there is one plane in the surface of mica from where the mica sheets will break off easily. So then the next thing that is comparable to cleavage is fracture. So cleavage, it can be good, it can be perfect, it can be not, it can be that cleavage is not present. Like for example, if you see certain minerals like hematite and all, there is no cleavage in them. Okay, so then next thing comes fracture. So what is a fracture? If the rock breaks along any plane, that is known as fracture. Breaking of mineral, not rock, breaking of mineral along any plane, that is known as a fracture. Okay, so then all minerals, they have different colors. So color is another property. You can see the color of the mineral and you can judge which mineral it is. Then you can see what form it is, like is it massive, is it tabular, does it have a nodular structure, does it have a mammillated structure, does it look like a bunch of grapes, so that thing. Then you have the luster. Luster is without the color, how does the metal look? How much does it shine? Does it shine like a pearl? Does it shine like a metal? Does it shine like diamond? So if it shines like pearl, it is called pearly luster. If it shines like metal, it is known as metallic luster. If it shines like diamond, it is known as adventitious luster. So what is adventitious luster? It's luster like diamond. So which mineral will have it? Zircon will have it. Zircon is your American diamond. So adventine luster is seen in zircon. Okay. So then after luster, another thing that we will see is that is streak. So when a geologist studies minerals, he has something known as a streak plate. Now streak plate is a plate of ceramic. Okay. So what happens? They take the streak plate and they rub the mineral on it. So when you rub something, it powders. The streak plate is very hard, so the mineral on it, it powders. Okay. So in streak, you see the color of the powder of the mineral. Color of powder of mineral. Okay, so that is what streak is. Now what happens is that when you see the streak of a mineral, at times streak is different from the actual color. So like this property of streak is mostly used to differentiate between hematite and magnetite. Now hematite and magnetite are really similar, just that magnetite is a little heavier than hematite, and their color is almost similar. They're almost, both of them are red to reddish black. So if you density, you cannot physically see and verify the density. So what you do is you take a streak plate, and but the streak of hematite is red, whereas the streak of magnetite is black. Okay, so this forms a basic difference between hematite and magnetite. Okay, so then next thing comes is the hardness. For hardness of minerals, we use a scale called Mohs scale of hardness. The scale goes from 1 to 10. The softest mineral is known as talc. So what happens in hardness is that this is a fact that the hard mineral will scratch the soft mineral, right? So if a mineral surface is scratched by some mineral, suppose hardness of talc is 1, whereas the hardness of diamond is 10. So the hardness goes from talc to diamond. There's a mineral called talc and there's a mineral called diamond. Everybody knows about diamond. So it goes from talc to diamond. So if somewhere in the middle you have feldspar. Okay, so if a mineral is if a mineral is scratched by feldspar, that means the hardness of mineral will be less than feldspar. Okay, so that is how we decide. Suppose a mineral is not scratched by number 9, that is corundum, it is scratched by number 10. So the mineral is less than 10, but it is, sorry, the hardness is less than 10, but it is greater than 9. So the hardness of mineral will be between 9 to 10. Okay, that is how we see the hardness. Okay, so these are the basic properties of different rock minerals. Now, what are the most common minerals? So before we go to that, there is another concept that I would like to share, and that is a concept of felsic and mafic. Felsic and mafic. So basically what are felsic? Felsic are dark colored minerals. So these are the minerals which are dark colored. They have black, brown, dark green colors. Okay, and sorry, mafic are dark colored minerals, and they have different colors which are dark colored, like black, brown and dark green. And when we come to felsic, these are light colored minerals. So mafic, they are dark colored minerals, and felsic, they are light color minerals. Light colored minerals such as, which have colors like white, light pink, very light yellow. Okay, so these are the mafic minerals and these are the felsic minerals. Okay, so now about some important minerals, we will group them into felsic and mafic. So the most important one, quartz, that's a felsic mineral. Then feldspars, they are felsic minerals. Okay, so these are the two most important felsic minerals, whereas the mafic ones, in this you have olivines, then you have pyroxenes. Okay, pyroxenes is denoted by PYX. Then you have amphiboles. So these are all mafic minerals. Now another thing that is more common in mafic minerals is a high content of iron like minerals, magnesium and iron like minerals. Okay, so they have a high content of heavy minerals, whereas in these you have silica and aluminium rich minerals. Okay, silica and aluminium rich minerals. Okay, and iron and magnesium, and of course silica is there. Silica has to be, it's common in almost all rocks. Okay, so these are the basic felsic and mafic minerals. Now the next thing, how we divide the minerals is on the basis of whether they are metallic, whether they are non-metallic. Okay, or if they are in metallic, are they ferro ferrous metals or non-ferrous metals. Okay, so first thing, on the basis of metallic nature. So on the basis of metallic nature, minerals are of two types: metallic and non-metallic. Now these metallic minerals, they are further divided into two types: ferrous and non-ferrous. Okay. So now what are ferrous minerals? That are found in association with iron and often mixed with iron. So these include, and these are the minerals which you mix with iron to form different types of steels. So these include manganese, chromium. Okay. And what are non-ferrous minerals? That are these include minerals like copper, aluminium, tin, zinc. Okay, so these are non-ferrous minerals. And what are non-metallic minerals? Non-metallic minerals are the minerals that do not contain any metal content. Isme you have sulfur, then you have phosphates. The phosphate deposits are there. These are used in making fertilizers. Then you have calcium carbonate, that is lime. So these are non-metallic minerals. Okay. So now we have discussed what minerals are. So now different elements, they combine to form minerals, and different minerals, they combine to form rocks. So now we will continue with what are rocks. So rocks are a aggregate of minerals. They are an aggregate of minerals. Okay. So now rocks are of three types: igneous, metamorphic, and lastly sedimentary. Okay, so these different rock types, they form different landforms, and the landforms are really dependent on the type of lithology that is present. So the type of rocks that are present in an area is known as the lithology of the area. The type of rocks present in the area is the lithology of the area. Okay. So now coming to igneous rocks. What are igneous rocks? Igneous rocks are the rocks which are formed directly by the magma. What is magma? That is the hot molten mass that is present within the surface of the earth. Okay. So the rocks which are formed directly from the magma are known as the igneous rocks. Now this magma, it can either cool at a depth within the surface of earth, or it can within the interior of the earth, or it can cool on the surface of the earth. Okay. So if it cools within the surface of the earth, it cools very slowly, obviously, because the temperature difference is not much high. So it cools very slowly, and it forms the minerals, they form large crystals because they have a time to grow. Okay, so these rocks that are cooled inside, they are known as plutonic. So these are plutonic rocks, they have large crystals. Okay, and the ones which cool on the surface, they are cooled very quickly. So what happens, the minerals do not get a perfect, they do not get timing to form perfect crystals. Okay, so this because of this lack of time, these rocks which are produced as, which are known as volcanic, they don't have, they have small or microscopic crystal, or what is known as that they can have an amorphous, they are known to have as amorphous structure. Amorphous structure. Okay, so that completes igneous rocks. So in igneous rocks, what are the example? So for volcanic rock, example could be glass or pumice, and for plutonic rocks, granite. Okay, so now what is pumice? Pumice is a very light rock. Pumice is a very light rock. Now what happens is that when the magma it cools, so what happens that all the gases that are inside the magma, they start to escape, right? So what will happen when the gases will escape, the bubbles will escape, so what will happen, small vesicles are left on the surface of the rock like this. So later these vesicles might be filled with some other minerals and form mimic but what happens in pumice is that because a lot of gas that escapes, it has a lot of vesicles inside of it, and hence it makes it a very light stone. Okay, and it even floats on the surface of water. Okay, so now the next type of rocks that we have to study, they are the metamorphic rocks. So now what are metamorphic rocks? Metamorphic rocks are the rocks which have been previously present on the surface of earth. When the previously present rocks on surface, they undergo pressure and temperature changes. They form metamorphic rocks. Okay, so now suppose calcium carbonate, CaCO3, limestone, it is a sedimentary rock. Now this was initially present on the surface of the earth, but then what happened, it got buried, it got under high pressure, and with depth the temperature also increased, and it got converted into what, marble. Okay, so that is what metamorphic rocks are, that they are the rocks which are initially present on the surface of the earth, but then they are subjected to high pressure and high temperature conditions, and then their structure and the crystal structure is changed, and because of that you have new type of rock which is known as a metamorphic rock. Now lastly you have sedimentary rocks. So now what happens is that with time there is a wear and tear of rocks. So these igneous rocks, these metamorphic rocks, okay, they break, they get weathered, they get eroded, and they are broken into finer particles, and these finer particles, the finer particles are known as sediments. Okay, so now these sediments, they go and they settle somewhere else, and from there slowly with time they are compacted and they form rocks. Okay, so these rocks that are formed from the broken sediments of igneous or metamorphic rocks, these are known as sedimentary rocks. Now one thing to remember here is that these sediments they are not always only from igneous and metamorphic rocks. Okay, these can come from other sedimentary rocks also. So whenever there is a previously present rock, igneous, metamorphic or sedimentary, what happens is that it breaks into different smaller particles. These smaller particles form sediments, and these sediments are transferred into sedimentary rocks. Okay, so now these are the different types of rock, and when igneous and sedimentary rocks, they undergo changes in pressure and temperature, they form metamorphic rocks. So again revising it, igneous rocks, they are formed directly by the magma. They are of two types. If they are cooled, they are solidified beneath the surface of earth, that is known as plutonic. If they solidify above the surface of earth, they are known as volcanic. Then you have the metamorphic rocks. Metamorphic rocks are the igneous and sedimentary rocks that have been subjected to pressure and temperature changes. Okay, so then next comes sedimentary rocks. When igneous, metamorphic and other sedimentary rocks, when they break, they form fine particles which are known as sediments. These sediments get deposited and then they get lithified. Lithified is the process of formation of rocks, lithification. So they get lithified and they form rocks known as sedimentary rocks. Okay, so this is igneous, metamorphic and sedimentary rocks. Now the beauty of earth is that every rock can be converted into every other type of rock, and this process in which any rock can be converted to any other type of rock is known as a rock cycle. Okay, so for our rock cycle, we will start first of all with igneous rocks. We will start with magma. Okay, so now this magma will solidify, and once it solidifies, what does it form? Igneous rocks. Okay, so magma, it comes out of the earth, it solidifies and it forms igneous rocks. Now what can happen? These igneous rocks can break, or the more technical term that we use is weather. Okay, so these igneous rocks, they weather, and if they break, what will they form? They will form sediments. Okay, now these sediments will join to form what? Sedimentary rocks. And now suppose these will be lithified. Now if they undergo pressure and temperature, what type of rocks will they form? They will form metamorphic rocks. Okay, now this metamorphic rock can again melt, and what will it form? Magma. If something melts, it will form magma again. Okay, so now this is one route to go about it. Then second route is that these sedimentary rocks can undergo melting and form magma. Okay, so from sedimentary you will have magma, and from magma you have igneous rocks. Okay, so now another thing that can happen is that these metamorphic rocks, can break. If these break, they will form sediments. Okay, and these sediments will be transferred into sedimentary rocks. Okay, so this is what is known as the rock cycle. Okay, and also igneous rocks can undergo pressure and temperature, and they can form sedimentary rocks. So you see, from here we are forming, from igneous rocks we are forming sedimentary and metamorphic. From metamorphic rocks we are forming igneous and sedimentary, and from sedimentary we are forming igneous and meta, because even the sedimentary rocks can undergo melting and form magma. Okay, so this process of in which every rock type can be converted into every other rock type is known as the rock cycle. So now the next thing that we have to study for today, this completes the topic of minerals and rocks, so the basic introduction to minerals and rocks. For the UPSC point of view, more than this, I don't think that would be required. So and it has not been asked so far. So now the next thing that we have to study is the interior structure of the earth. Okay, but again in the previous lecture we had discussed about the direct and indirect ways to study the interior of the earth. In direct ways we had included volcanism and earthquakes, whereas in indirect ways we had included other things such as uh, the gravity survey, magnetic survey, or density survey. Okay, so that those are the indirect ways. So now in the direct ways we have two things: earthquakes and volcanoes. So earthquakes is the first thing that we will study. So now earthquakes, since it's the first thing that we have to study, and it is in news a lot these days because of the Himalayan earthquakes, so the topic of earthquakes becomes very, very important. Okay, so now what is the first thing is that, again, whenever you study something, you should ask yourself the WH questions, that is what, when, why, where, and how. Okay, so these are the WH questions. So whenever you read something new, you should ask yourself these questions, and that will almost cover every topic. So what is the first question? That what is an earthquake? So earthquake is it's a vibration of the earth. What is earthquake? Earthquake is the vibration of the earth. Why is it produced? Produced by rapid release of energy. Okay, So earthquake, what is an earthquake? Earthquake is the vibration of the earth produced by rapid release of energy. So now why is this energy released? Why is this earth releasing so much of energy suddenly? So what happens is that earth is a very dynamic place. Okay, every continent, every plate is moving, as we'll study in the plate tectonic theory. So it is all moving, nothing is constantly stable. So because of this movement, suppose at earthquakes, the first thing that we study is the earthquakes related to faults. Okay, so what are faults? Faults are the it's a crack in the surface of the earth where the two sides of the crack, they are moving in the opposite, they are sliding past each other. Okay, so now what happens because of this, if here is a transfer boundary, what will happen? There is so much of rock pressure above it, there is friction amongst the rocks, so this is not able to move freely. But at times what can happen, that this force of sliding, it can overcome the friction and it can overcome the pressure of the overlying rocks. So because of that, they will move. So now it had so much of energy that is released because of this movement, and because of this movement you have earthquakes. So again, along the faults, because of the friction and the pressure of the overlying material, rocks are generally not able to move. But when they do, when they can overcome that friction and that pressure, then you have earthquakes. Okay, so now next thing is the very basic terminology of an earthquake. So the first thing, where the exact point where the energy is released, that is known as the focus. Okay, so the point where energy is released, focus is the point where energy is released. Okay, focus is also known as the hypocenter. Okay, so this can be, focus can be close to the surface of earth, this is the ground surface. This can be close to the surface of earth, it can be at depth, or it can be very very deep. So like that we have shallow focus, earthquake, intermediate earthquake, and deep earthquakes. So obviously, as it must be evident from now by common sense, that obviously something shallow focus will have a more destructive effect on the human settlements. Okay, the deeper it is, obviously the waves take time, and by the time they reach the surface of the earth, their effect has been drastically reduced. Okay, so now this is the focus. Now one thing that here you should know is, if there is a point on the earth, the diametrically opposite point is known as its antipole. Okay, if there is a point P on the earth, the point diametrically opposite P dash is known as its antipole. So if the focus of the earthquake is, what happens is, if the focus, right above the focus, there is a point called epicenter. Okay, so if you travel directly from the focus to the epicenter, to the surface of the earth, to the point which is directly over the focus is known as the epicenter. Okay, so now the point which is diametrically opposite to the epicenter on the surface of the earth, suppose here you have the epicenter, so the point which is diametrically opposite is known as anti-center. So diametrically opposite point to the epicenter is known as the anti-center. Now, another thing that you have to see is that as you keep going away from the focus and the epicenter, the effect of the earthquake waves keeps on decreasing and decreasing. As we move away from the focus and the epicenter of the surface, the epicenter of the earthquake, the effect of earthquake waves keeps on going on decreasing. Okay, so now the next thing is, again to revise, first of all, what is a focus? Focus is the point within the surface of, beneath the surface of the earth, where the earthquake, where the energy is released. The point directly over the focus is known as the epicenter. The point diametrically opposite the epicenter is known as the anti-center. Okay. So now to discuss that how the earthquakes actually happen, there was a scientist named Reed. he gave a theory which is known as the he gave a hypothesis known as the elastic rebound hypothesis. So now, according to the elastic rebound hypothesis, he said that rocks, they behave in an elastic manner. So like if you pull a rubber band and then you leave it, so what happens? When you pull it, elastic energy is stored in it. When you leave it, what happens? It jumps, so the elastic energy is released. Okay, so now the same thing happens with rocks. He said that rocks, they behave in an elastic manner. Okay, so this elastic rebound hypothesis was given by Reed. And what did he say? For this, he gave an analogy of a limber stick. Okay, so now he said that this is the original position of the rocks. Okay, so now this is the original position of the rocks, and this is the fault where there is a crack within the surface of the earth. So right now there is nothing happening. The fault is there, no movement is there. This is the original position of the rock. So just like that, you have a stick in both your hands, and this is the original position. You are not putting it under any stress. Okay, now this part of this side of the fault, it begins to move in this direction. So what will happen? Elastic energy will start getting stored in the rocks, and it, how can you compare it? Take the stick and bend it. So now again, elastic energy stored in the rod, in the stick also. So that is how elastic energy begins to be stored. Okay, so these plates are moving in opposite direction. Elastic energy within the rocks on this fault line, it's being stored. Now what will happen? All of a sudden these plates will slip besides each other, and what will happen to the stick? It will break. So when it will break, when it will take a stick to break it, what happens? The two parts, they start to vibrate. Okay, so just like that, earth, the two parts will start to vibrate. Okay, and this is known as the elastic energy which is released by the rock, and by the rupture, it means the breakage, so elastic energy is released, and within this stage you have the earthquakes. Okay. Now once the energy is released, what will happen? They will again come to a position which is static, and they are stable in that position. But again, when again the slippage will happen, again energy, again deformation, again slippage, and again release of energy will happen. Okay, so now you see here the energy is released, vibrations are happening here and here, right? But when they have again come down to static position, energy is not released, and they are two ruptured parts which are stable. Okay, so this is the elastic rebound theory. So now, how do scientists know about this earthquake, and how do they study the earthquake? So for that, you have instruments called, there are instruments which are called seismographs. Okay, so these are the instruments which are used to study the earthquake waves. Okay, so the earthquake energy travels like waves. Okay, so these are instruments which are which are used to study the earthquake waves. They are known as seismographs, and the records that these instruments produce are called seismograms. Okay, so the records that these instruments produce, they are known as seismograms. Okay, so now what do these seismograms show us? These seismograms, they show us two types of waves. One is body waves and one is surface waves. Okay, another thing that happens during an earthquake is that while there is a major earthquake, there can be smaller earthquakes which are preceding the earthquake. That is, they happen before the major earthquakes. So those are known as foreshocks. And Why do they happen? Because major energy stability has been done by the earthquake, but the minor adjustments before and after the earthquake can happen. So the minor adjustments before are known as foreshocks, and the minor adjustments after are known as aftershocks. Okay, so the waves from the foreshocks and aftershocks are also studied. So now again coming back to the waves, there are of two types, body waves and surface waves. So as the name suggests, body waves, they travel within the body, and surface waves, they travel within, and the surface waves, they travel on the surface. Okay, so now what happens is that earth energy is when energy is released from this focus. Okay, so what happens? Body waves are released. Okay, now these body waves, they interact with body waves interact with surface rocks, and when they interact with surface rocks, they form surface waves. Okay, so body waves are released at the point of focus. When these body waves, they interact with the surface rocks, they form surface waves. Okay, so now there are body waves are of two types, P waves and S waves. So these are the two type of body waves that are very useful to us in studying the structure of the earth. Now next is the surface waves. They are R and L, railing and love waves. Okay, so but surface waves, first of all, their transmission is very complicated, and as far as structure and interior is concerned, we study the P waves and the S waves. Okay, so now coming to P waves. So P waves, they travel by compression and expansion. So this figure shows compression and expansion in a slinky, which is a long spring. So what happens? P waves, they travel like sound waves. Okay, so P waves, they travel like sound waves. They move the waves. They give energy to the particles, and the particles, they compress, they expand, compress and expand. So these set of particles, they will compress. Then they will transmit energy to next set of particles. So they will expand, and the next set will compress. Okay, so that is how the P waves move. So you see in the slinky. So initially it is at rest. So what will happen? When you push it, the some part will be highly compressed and some part will be expanded. This part will compress this part, and then this part becomes normal and this part expands and this part compresses. So that is how it keeps transferring. Compression, expansion, compression, expansion. So now the particles are moving in the direction of the wave. The wave is progressing in this direction, and the particles are also moving in this direction. The wave is going in this direction. Expansion is also happening in this direction, right? So that is what happens, that in the P waves, the particles move by compression and expansion, and the direction of particle motion is parallel to the direction of wave motion. Now the another thing that is more important to remember about the waves is that they travel through solids, liquids and gases. So they travel through all the three mediums, solid, liquid and gases. So again, now you see that when P waves are moving below the surface of the earth by compression, expansion, the black parts represent compression and the light ones represent expansion. So it will have the same effect on the surface of earth also. This part compressed, expands, cracks, compress, expand. Okay, so like that. So now coming to S waves. So how do S waves move? That if you take a rope and tie one end of the rope on the surface and you give a jerk on the other end. So how will the material move? The particles will move perpendicular to the direction of wave motion, and this is where particles are going up and down. So the particle motion is perpendicular to the wave direction. Okay, so that is how the S waves move. In the P waves, particle motion is parallel to the direction of wave propagation, whereas in S waves, the particle motion is perpendicular to the direction of wave propagation. Now, S waves, they can, here the important properties is that they travel through solids only. Okay, so S waves, they travel through solids only. Now you see the particles are moving up and down. So this is the place the particles are moving up. So and a crest-like surface is created. Then they move down. So a trough-like. So this is how it affects, has an effect, a wave-like effect on the surface of the earth. Okay. So now since we have seen that the surface of the so this is a more clear diagram of the P waves. So here you can see it clearly how this part is being compressed, this is expanding, and how wave is propagated by expansion. Okay. Now next thing is the P and S wave shadow zone. So now we have already established that the P waves and the S waves, they travel through different mediums. Okay. Now also P waves are faster. In fact, it is said that if the P waves are and S waves, they are traveling through the same medium. If the medium of propagation is the same, then the speed of P waves is 1.7 times the speed of S waves. Okay, so the speeds of P waves is almost twice the speed of S waves. Okay, yeah. Okay, so the P waves are almost twice the speed, twice the speed of S waves. Okay, now what happens that the part of the earth which is solid, from that both P and S waves will pass. So this part of the earth, so we are here, crust, mantle and core. So now the mantle is also, so this part is the crust, mantle and core. Okay, so now the waves P and S waves, they pass through upper portion of, uppermost layer of, okay, the uppermost layer is solid enough to let the S waves pass. Okay, so the that layer is known as the asthenosphere. Okay, though we will discuss it later. So what happens, whatever part of the earth is solid, from that both P waves and S waves will pass. Okay, the dark ones, they represent P waves, and the light the dark one represents S waves, and the light one represents P waves. So now in this region both P and S waves are passing, but beyond this region, what will happen beyond this region? What is happening? S waves are not passing. So because of this, there is a shadow zone for S waves. That means no S waves are recorded in this direction. So that represents beyond 103 to 105 degrees. 103 degrees to 105 degrees zone is known as the S wave shadow zone, because the S rays cannot travel through the liquids. Okay, so now again you see what happens. So one thing is that they cannot travel. Then next thing is the waves get refracted. Now what happens that the wave wants to maintain its velocity. So it when it goes to a denser medium, what it does is it cuts shorts its path. Why? Because it says that now I know that there will be more molecules which I have to encounter. So then what will I do? I will make my path short so that I can travel through the same speed. So there is a bending of wave. Suppose this is a lighter medium and this is the denser medium. So the wave is coming along this direction. So the wave is coming along this direction. Okay, so technically it should have gone like this in this medium, but it cuts short its path and it is bent. Okay, so now what happens that the part of the earth is some part of the earth next when we get into the deeper mantle or the in outer core, what happens, it is very dense. So these P waves, they are bent at this boundary, and then again when they enter the solid inner core, again they are bent, so they are refracted at the boundary of high density. When they encounter high density materials. Okay, so then what happens between 103 or 105 degrees to 140 to 145 degrees,